30 days of machine learning. Today we are solving insurance expense prediction problem using a gradient boosting regressor. Okay. Too much to do in this day and in this problem statement. This is a very heavy problem statement, and just we are going to be exploring a lot of concepts today. So, without wasting any time, let's just dive into it. First things first, we'll start with our original pattern as we move forward. First of all, what problem do we have on our hands? Insurance expense predictions. So we all know what insurance is. It is a very vital concept in especially in medical and educational expenses. I mean, insurance exists for many things, but I think medical insurance is probably one of the most widely used applications of insurance. Okay. So we have got different types of insurance schemes out there, which are lent to different customers. And basically, there are different companies offering different insurance schemes, and the customers select one or two and give their money off to the company. So it becomes very important for us to predict what charges, an insurance company will probably have, because that is what determines as to how many customers it is going to have. If the insurance is underpriced, okay, if it is too low, then it will just lead to losses to the company, which is like a business loss. Okay, it's just unacceptable. We never want that. If the insurance is overpriced, then what's going to happen is that customers are going to churn, which means they're going to leave, which is again going to bring unexpected losses to the organization. So our goal in here is to use old data, historical data of different customers and their insurance prices in order to predict future prices for the customers. And we need to be as accurate as possible. Okay. Again, see, one single value of insurance price will not exist, which is the best value. It all depends on what specific customer we are dealing with based on all the factors that we have. So, keeping that in mind, we move forward. Okay. So we have done our typical pipeline in this case, started from the EDA, analyzed the data, then moved on to the model physics and eventually analyzing everything. Okay. So this is the data set. It's the insurance.csv data. CSV means comma separated value. So it's like an Excel file. It will be available in Kaggle. So I've not really put the link in here. This is like a very naive data set. Okay. And this is a tabular data. So 1338 records, which means 1338 rows, and 7 features means 7 columns. And this is the target column, which means the one that we have to predict, the dependent feature. The others are the independent features. Okay. Can go look at the data. I have not really shared it here. It's very simple to understand. These are the types of all the data. Age is numeric. Gender is categorical, either male or female. So maybe you can categorize it as 0 as 1, simple again. Okay. And yeah, this is what we did in the data preprocessing pipeline. So, these features can be categorized as binary features, 0, 1 type of features. So the person is either a smoker or not, 0 or 1. Okay. And if the person is in the US or outside the US, that is again 0 or 1. And the gender or the sex again, 0 or 1. So these are very typical, data pre-processing steps that we do. So we move on and let me show it to you in the code. So this is very basic stuff. Uh, the two goats of machine learning, NumPy and Pandas, nothing happens without them. These two are for the visualization. Time I've used to measure the inference latency, which we'll discuss later. This is the one hot encoding standard scaler. Okay. GridSearchCV. Oh, I've taken it twice by mistake. This is for the hyperparameter tuning part. Print test split typical. This is the model that we will be using. Don't worry, I'll be explaining everything in detail. Okay. These are the two metrics, the most important metrics in this problem. Okay. Now, you know, discussing this problem statement, we need to be absolutely careful about one thing. Since this is a prediction kind of a problem, uh, it will eventually be a regression kind of a problem statement. Okay. So till now we have covered a lot of classification type of problem statements where we are classifying one thing as either type 1 or type 0, which is binary classification. Okay. So this is a very vital regression kind of a problem statement. And regression problem statements from the first look, they seem very easy and very naive. But this one has a lot of complications, which I'll be discussing. So let me go back to the code again. So this is how import the data set. Okay. So you can download your CSV file and you can put it in here and then copy the path and paste it between these quotes right here to get it. Okay. This is the typical keyword to do it. We have discussed this many times now. We have encoded the categorical features right here. Drop first is equal to true. We know this very important. This is so that we avoid the dummy variable trap, because we only need two variables in order to encode them. Because let's say that we have gender. Now we know there are two genders, male and female. It means that if male is encoded as 0, female will automatically be encoded as the opposite of 0, which is 1. We don't need to keep two variables to encode it. So we drop one of them to avoid the dummy variable trap, which is why we have got this drop first is equal to true. Again, I've discussed these things before. We drop expenses because it is the feature that we are predicting, so we keep it separately. Okay. I have done the EDA and then commented it out because the EDA is not responsible for the training, it is just for the developer. So this is what we have done. A pair plot has been plotted. I will be showing you that. This is very important and again a very typical idea in the EDA. So we are basically drawing a heat plot or a heat map. It is using the Seaborn library. Okay. And it basically is printing the feature correlations amongst all of these features that we have. So whether how largely or how little these features are correlated with each other is what the heat map is going to show us. Cool warm basically means the features which are highly correlated will be very dark in color, and the ones which are not will be very less. And not is equal to true will give us the numbers inside it, and CORR stands for correlation. Okay, so if I open the correlation, so this is the heat map printed. So we wrote the and not is equal to true. So if I did not write this and not is equal to true, I will not get these numbers written inside the squares. Okay. And not is equal to true gives me the numbers written inside. So these are the values of the correlations. So you will ask why this is one. So age correlated with age will obviously be one because they are the same variables. Okay. And you can look at other columns as well. So this is pretty dark. This means they're negatively correlated. The value of correlation lies anywhere between -1 and 1. This is a very dark column as well. Smoker and expenses are very highly correlated. Smoker and expenses, you can see this again. So this is how you can read it. This is a typical idea in order to understand the data set that we're dealing with. Because if features are highly correlated, then your model training will be affected. Here it is fine because it's just the typical correlations. Okay. So this is it for the EDA. We have not done anything too special. Okay, this is the train test split, standard 80-20 split that we make. Test size is 0.2, which means 20%. Training will be 80%. Random state is equal to 42, gives us reproducible results. Okay. So now comes the main part. Now comes the concept involved. Okay. We'll go into this very slowly. Till now, what I have just discussed is what we have done in all of the past 7 models that we have discussed till now. And we will be doing it too because the EDA, the pre-processing, the data loading, this is the typical part in all of the pipelines. Now comes the uniqueness. Now comes as to what did we actually do. Okay. So let me come back to the board slowly. Okay. So as the EDA, you can read all of this by the way. These are typical things that we have done. This is a pair plot that I printed. Okay, you can interpret it. It's pretty simple. So pair plot gives you basically the plot between the different features. So you can see expenses is right skewed here. Right skewed means that the right values are very less compared to the left ones. Now this means that the individuals with high expenses are very less in number. So you can use it to interpret as well. This is pretty typical. Okay. Okay. This is another scatter plot to this expenses scatter plot as well. You can use it. Now comes the main thing slowly. Okay. You can read this all later, but first I want you to quickly listen to me. So, let me take out the pen for a second. Simple. Yeah. So very important, slowly. So as I said that currently the problem that we are solving in here is a regression problem statement. We have got to find like the best fit line. That is what regression wants us to do. We have got X and we want to predict Y from it using some past historical data. We are not classifying here. We are using regression. Okay. So whenever we talk regression, a typical idea and a very simple, straightforward idea that comes to mind is linear regression. Why not apply the simplest and the easiest form of linear regression? Let's just go forward with it. But the thing is, here comes the catch. Linear regression will be the wrong choice here. Okay. Why is it? So let's analyze slowly. So, like I said, when we look at insurance data and, when we go back to the feature correlations, we see that the features are, they're hardly correlated. See these values of correlations, 0.00041, 0.01, these are very small values of correlations. We can say that the features are almost independent with each other. They do not depend upon each other at all, hardly, except for maybe this expenses and smoker value, which also does not matter because it is just one feature. So, this data, you can say that this data set has a lot of non-linear relationships. Okay, relationships which do not look like this. Relationships which do not look like, sorry, relationships which do not look like a straight line. Okay. So like a linear relationship can be, something like this. This is a linear relationship. The green line is y is equals to mx plus c. This is how we expect linear regression models to work like. They are brutally simple. We have got x and, you have to predict y from it. So the closer you are to this line, the more accurate your model is. But the relationships in this data set are not like this. They may be like in a wavy shape or in a different shape altogether. So linear regression will fail here, okay? Or like it will struggle here. The accuracy will be very low, R2 score will be very low. So these things will happen. Now comes a very important question. What should we use here? So another idea that we can use here is maybe like a decision tree model. Now, why is that? Why go for a decision tree kind of a model? It's pretty simple. A decision tree model creates splits based on the different types of features that it has, and it follows one of two algorithms. So either it will follow the ID3 algorithm, okay, or it will follow the C45 or wait a second, the ID3 or C45. This is the name of an algorithm. No need to memorize it. I just like stating it. Or it will be using the CART algorithm. Okay. In the CART algorithm, we calculate nothing but the Gini impurity. Okay. The Gini impurity, where you calculate nothing but sorry, calculate nothing but the probability score. So it looks something like this. Okay. P of I is the probability score calculated for the ith feature. Okay. And then in the ID3, we calculate the entropy. Then we calculate the gain using the entropy. The basic formula is negative of P log P. Okay. Log of base 2. This is what we do here. Okay. And we can use any of them. CART is more popular because it just calculates the probability values and then, the highest values chosen to create the split. And eventually, we have discussed this before as well. Uh, okay, just a second. Let me erase. This is the old one. I forgot to take a new sheet. We'll take it later. Okay. And as we discussed in the decision tree, I think on day two and in the random forest that we built as well, that the time complexity comes out to be nothing but we go of n log n. Because after we have had the information gain or the entropy values, And in the cart, after we've had this value right here, we take the maximum one. So for that, we have to sort and then take the maximum value. And sorting takes nothing but n log n. Okay. So maybe we can use a decision tree as well. Okay, it is valid. But here comes another big concept that I wanted to mention here. So, of course, we will not be using a decision tree in this case. We open new sheet. Okay. Okay. So we will not be using a decision tree here. And here comes a very important concept that we need to discuss. So why not a single decision tree? What is the issue with a single decision tree? The thing is that whenever complicated data is involved, like we have in this case, where there are lots of non-linear relationship, decision tree might cause overfitting. Okay. So whenever we are dealing with a single decision tree, especially in the case of regression problems like we are right now, what happens is that there is a massive risk of overfitting involved, where basically the data where the single decision tree almost memorizes the training data, and hence the training accuracy is very high, whereas the test accuracy is pretty low. And the variance is very high. The model is not at all generalizable. So the decision tree here fails. Rather, what we try and push for is a random forest kind of an approach. So random forest is nothing but a collection of decision trees. Okay, nothing but a collection of decision trees where lots of individual decision trees are used, and then later we can average out their predictions. So if we have got, let's say, five decision trees, there can be as many. So we have got dt1, dt2, 3, and so on. So we get different decision trees like this. We take the prediction from all of them and we average it out to get our answer, or maybe we do some sort of a voting algorithm, and then we average, and then we take the final prediction as the answer. Okay, so this is like a random forest sort of an approach. And why use a random forest? Because random forest uses multiple trees to ensure that there is a random selection of a subset of features. And that way the predictions are aggregated later, and the results are far more interpretable and generalizable. So the risk of overfitting is comparatively very less, because what's happening in overfitting is that the model basically memorizes the training data. Now, what random forest is doing is that it is saying that I will be taking a different subset of features every time. Okay, so let me show this to you quickly to avoid any confusion. Now, this was our entire data. Imagine this as our data. Okay, this is 80% of it. This is 20% of it. Okay, this is the testing data, typical. You can choose a different ratio as well, but the point will remain the same. This is our training data. Now, a decision tree model will be choosing this every time. Okay, and hence, what will happen is it will slowly memorize this data. And hence, the accuracy on this data will be very high, and accuracy on this data will be very low. We don't want that. Now, with random forest, what it will do is it will choose a different 80% every time. Okay. It means, let's say, for the first time, it chose this 80%. For the next time, let's say that it chose 80% from this side. Now, next time, let's say it chose the 80% in the middle. So every time a different subset of features will be considered. And in the end, obviously, the predictions that we get to get the final prediction will be averaged to get our final output. So that way, we can prevent overfitting and get a very generalizable model at the same time. This is why. Whenever we have data which is non-linear and tabular in nature, random forest will always be better and will always give us more generalized results than a decision tree. Okay. But it is still not done. Now, will we be using a random forest model here? No, no, sorry. Nada. Zip. Why? Now comes the most important part of the video. Okay. So let me to explain why we will not be using a random forest model. Let me quickly get to the board again. Now I'll have to introduce you to a concept, a very important concept. It is nothing but the concept of ensemble learning. Sorry. Okay. So, what the hell is ensemble learning? Let's discuss it. So, ensemble learning is it's one of the most popular concepts in machine learning. And to explain it simply, an ensemble is nothing but a group. Okay. An ensemble is nothing but a group. And learning is like learning that happens in any machine learning model. So now what happens in ensemble learning is that, we combine multiple weak models to get a final decision. Okay, so let me write it down so that we don't miss any of the info. Combine multiple weak models to get a final decision. Okay, this is what an ensemble learning does. This is like the simplest way I can, put it forward. Combine many weak models to get a result. Now, what's the intuition here? Why are we doing this? Why are we not going for a single model which gives us very, high quality results? So this is the problem here. Like I said, that we have got data in our problem statement, which is highly non-linear. Okay. It has relationships which cannot be mapped in simple XY form. So in this case, our main motive is that, we train, rather than getting one highly accurate model, what we try is that we get multiple models, base models, weak models that make lots of errors. We are not going for one strong model. We are rather saying that, you train five different models, which make lots of mistakes, which have lots of errors. And then later, we can create a model which learns from the previous mistakes and is strong. Okay, that is the point here. So let me show it to you diagrammatically as to, what does a typical ensemble learning model look like. So it's a very simple diagram. So, I've got a rectangle here. It is like this. Okay. Now, this will contain nothing but this is bad. This will contain nothing but the input. Okay. Simple. The input data. Now what? Now comes the main thing. Now what's going to happen? Now, inside here, I'm going to have multiple smaller models. Okay, let me take this. So I have got, let's say, one, two, okay, three, four, and five. So I've got five base models. Okay, what are these base models? What do we put in this? I'll tell you everything, but just hear me out right now. We have got five very weak models. They can be anything, but the thing is, I know for sure they are very simple and very weak, which means I know that if I use any one of them alone, it will not give me good results. Simply like we used a decision tree model. So let me call it, sorry, let me call it L1 as, learner 1, learner 2, 3, 4, and 5. Okay. And they're not working individually. I'll tell you how they work. This is the collection of the models that I'm running. Okay. These are my base models, okay? And then the input is fed to the base models. Now, like I said that, when these models give out a prediction, so L1 will, please scroll up a little bit. So L1 will give me some prediction. L2 will give me some prediction. L3 will give me some prediction. Similarly, L4 and L5. So we then use another model or some sort of a voting algorithm to decide as to what will be the final solution. Now that algorithm that we are using to, predict the final solution, it is called as a meta learner. Okay. No need to get overwhelmed with these words. These are just words. A meta learner, I'll just explain it quickly. So like I said that, we are getting a different prediction from all of these 5 week models. Now, which one should we decide? Which mechanism should we use to decide? Is it voting, or do we combine it, or do we use it sequentially? Maybe we use a logistic regression to decide it. We can use anything. That mechanism that we use is called as a meta learner. Okay, to decide as to what prediction out of these five or which mechanism to select. Okay, now the meta learner sends this back, as to what should we choose from all of them. We can also use a weighted sum where, predictions from all of them are combined based on how correct they are. That is also a solution to do. And then, we get nothing but go here and we make another quick rectangle. We get an output. Okay, the output that we wanted, the final output. Okay, so this is how the basic idea of ensemble learning looks like. The point is that, we are saying that, okay, we cannot go and simply ask for a very strong model straight away, like one which works all the time. So what we are doing is we are saying, okay, I'm taking these 5 weak models and I'm combining their predictions somehow. What's that somehow mechanism? I'll be telling you that, but I'm going to combine them somehow in order to get a final answer. And that final answer will be very strong. Why? Why? Because it is based on the mistakes that these 5 models are making. Okay, understand this very nicely. These 5 are very weak models. They are stupid models. They will never give me a correct answer. And I know that, which is why I've chosen that. But I also know that these models will be making mistakes. And I will be training my final model based on their mistakes so that the final model is highly accurate. Okay, it's like, let's say you are participating in a race. You want to prepare one very strong Formula 1 car for your race. So you know something about the track conditions, something about the weather, something about a driver, but nothing is clear. So what do? You take 5 different cars, okay, and you race them in races that don't matter, normal races, and then you evaluate the mistakes that all of the cars made, and based on those mistakes, you make one final car that will definitely be the best one go forward with. That is the intuition here that ensemble learning works with. Okay. So now let me quickly go on to the next thing, which is very important, which is, what are the types of ensemble learning? This is where, we'll be connecting from our old question. And what was our old question? That we are not using random forest here. Why? So I'll just quickly get on to that. So, when I write ensemble, quickly let me write it down. Okay, so I'm writing ensemble learning as EL to save time. So when I write ensemble learning, there are many different types to do it. So, I'll be listing them as a universal type. So you can use them to describe in an interview, or you can use them anywhere basically. I mean, these are the 5 types that I have heard, but the popular ones are just two or three. Okay. So type one, we have got bagging. Okay. Type 2, we have got boosting. Type 3, we have voting. Okay. Type 4, we have got stacking. And type 5, which is hardly used, but it is still worth mentioning, we have got blending. Okay. So, I will be focusing mostly on these two, boosting and bagging, because they are the most popular ones and they are the ones which are used in production most of the time. Voting, stacking, and blending are just small modification techniques. So, since I'm majorly discussing only boosting and bagging, I have attached an article in the description that you can check out for to read about all of them. Okay. So if you're interested, you can check out the article. It is not written by me. I think it's a Medium article. You can check it and read about all of them. But the most important ones to stress out for, if you are aiming for an interview or if you're aiming just to strengthen your machine learning knowledge, it is boosting and bagging. And I'll be getting on to why is that. So when I write boosting and bagging, bagging does not have types. Boosting does have different types. Let me quickly write down the types of boosting, which will eventually bring us to the model that we are going to be using today. So we have got GB, which is gradient boosting. Okay. We have got ADA boost, which is adaptive gradient boosting. Okay. We have got CAT boost, which is categorical boosting. Okay. Then we have got LGB, which is light gradient boosting. And finally, the daddy of all daddies, the it's like, the holy grail of boosting algorithms. This is the GOAT. This is the one which is the most important. XG boost. Okay. Now, what we have implemented today is the gradient boost model, and to improve and to show the strength of XGBoost, what I have done is that tomorrow I have trained the XGBoost model and explained it end to end on this same data set, on this same problem that we are discussing today. Okay, but that's not the point right now. Let's first discuss what we are doing today. So, ADA Boost, I have not specifically discussed in this series. You can read about it in the article, but it is very intuitive and simple to understand. Cat boost is based on categorically boosting the gradients. This is light gradient boosting, so it is nothing but a lighter version of what we are implementing today, which is gradient boosting. XG boost is the most mathematically superior. It's so magnificent. It is a very elegant model to interpret, which is why this becomes the most important. If you have tabular data that you are working with, and your data set is within 10 million rows, which means the number of entries in your tabular data is less than 10 million, then always, even in production level pipelines, we go for an XG boost kind of a solution. If it exceeds 10 million, then we eventually opt for more complicated deep learning solutions, but till then XG boost is the one to implement, which I'll be explaining in the next day. Now let's continue on with our discussion. So, we have got boosting and bagging. Now, the most important thing comes in. What is boosting and bagging? What's happening in here? So, very important and easy to understand. So, bagging, the purpose of bagging is that, we create different subsets from the data and, from the training data. And then what we do is we combine them. We choose data randomly, which is used to train the model. And in the end, what we do is we average all of the predictions to get our final answer. That is what happens in bagging. In boosting, what we do is we make a strong classifier from a number of weaker ones. And what we say to the model is that, each model will learn from the mistakes of the past model. Okay, so let me write it down to avoid any confusion. Okay, quickly. Yeah. So if I write here bagging. So in bagging, we are doing nothing but, bagging will be to, we will create subsets of data from training data itself, training of data. Okay. And we average all predictions to get final output. Okay. Now, very simple. Boosting. So boosting, you can hear it in your ears. Boosting is like boosting. So like one model makes an error and the second one tries to correct it. Then the third one tries to correct the errors of the second. Then the fourth tries to correct the errors of the third. And so on we go and we keep going until the error has converged, which means that we have obtained a highly accurate model or the maximum number of models have been added. So in boosting, create a strong model from a series of weak ones, okay, where each weak model tries correcting errors of previous. Okay, this is what's happening. Now you can write it down. You can just look at it, whatever. So the point here was to explain. Okay, so again, just to quickly revise so that we have not lost the context. Ensemble learning, we have got these five types that we have discussed. I'm only stressing on the first two. This is boosting and bagging. So bagging, the full form of bagging is bootstrap aggregating. It doesn't make much sense here to discuss the full form, but I just wanted to mention it out. Okay. This is the boosting. Now, very important, quickly read the definition of bagging. What is bagging saying? It is saying that we are creating subsets of data from the training and we are averaging all of them to get final output. Now, isn't this sounding similar? Yes, it is. It is sounding similar to what we discussed right here in the random forest model. Okay. Because the random forest is doing a similar thing. What is random forest doing? Random forest is saying that I'm going to take a different subset of features from training so that, overfitting is reduced, variance is reduced, and then I can get my final output as the average of all of the predictions. So that is it actually. That is the correct intuition for it. So bagging is implemented using random forest. So whenever I am implementing a random forest regressor or a random forest classifier from sklearn, I am basically implementing bagging method of ensemble learning. Okay. So, we did random forest, I think, on one of the earlier days in this 30-day machine learning series. But I didn't mention that the random forest is like a ensemble learning technique because there it was too much out of context. Today, it makes much more sense mentioning it, which is why I've added this discussion in here. Okay. So, this is it. And boosting is completely separate. Boosting, if I try and specify, you can take this is like your weak learner one. It You train it and it makes some mistakes. Then we take another weak learner two. We train it, it makes some mistakes, and it learns from the mistakes of this first one. Then we take the third one. Now the third one learns from the mistakes of this one. And eventually we keep doing this until we obtain a highly accurate model, or we reach the maximum number of weak learners, because we cannot just randomly keep adding models. It will lead to overfitting and too much of computation power that we require. So this is what's going to happen. So, this is why it is very important. Now comes the question, which is part of our original question that I wanted to discuss. Why not random forest? Okay. It's a very simple question. See, we have already decided that linear regression is not going to work here. Okay, so no linear regression. Then we try for a decision tree. No, because it is too simple, it will overfit and it is just not suitable here. Okay, then let's go for a collection of decision trees, which is very intuitively a random forest model. So then I said, no, not random forest. Now, why not random forest? Now, look at this definition here. A random forest is just an implementation of bagging ensemble learning. So we are creating subsets and we are averaging out the predictions. But the thing is, these types of models are not very accurate in the case of problem statement like ours, which means whenever we are dealing with tabular data, such as insurance prediction, we do not go for approaches similar to bagging. We try for approaches similar to boosting. Why is that? Because this is much more intuitive to fit in our case. We first train a weak learner. Okay, so let's say our weak learner is a like a small decision tree, and of course it will make some mistakes. Then the second decision tree learns from the first, and the third learns from the second, and so on. Okay, whereas this bagging approach here still sounds very naive because it is just it is just taking different parts of the training data set, and it is not doing us much. So it is very important to understand that boosting approach here will be far stronger because we are dealing with a tabular data set and non-linear relationships. So if you want to reason as to why we are using boosting here, it is because we have many non-linear relationships and a very clean tabular data set to use from. Okay, this is why we go for boosting sort of an approach. So now, I have covered the definition, but I think I will cover this because it makes much more sense in discussing it. So let's quickly discuss the difference between bagging and boosting. This is asked very popularly in college examinations. It was asked in mine as well, which is why I'm quickly discussing it. So, like I said, we have got bagging and boosting. Yeah. So we have got bagging. So what's happening in bagging is that we are taking a different subset of the training data every time. And why do we do that? So that the model does not overfit. So can be said very similarly. Bagging will be used when variance is high. And naturally, boosting will be used when bias is high. Okay. Okay. Bagging will, you know, prevent overfitting. Boosting will prevent underfitting. Okay. Very simple till now. Moving on. Uh, so bagging trains models parallelly. Okay. Boosting trains them in a sequentially. Okay. One learns from the error of the others. So sequentially, let me write it in short. Sequential. Okay. So very important thing again. Boosting, just a second, increase this line. Boosting uses different type, very important thing. Boosting combines different types of predictions. Okay. Hence capturing, nonlinear relationships better than bagging. Whereas bagging combines similar types of predictions. Okay. These are the key differences. Now, without moving too far from the context, let me quickly get back to what we were solving. So, till now, we have discussed why a linear regression problem will, of course, be too naive for this data, and of course why a decision tree will overfit and why we need to go for some better approach. Then we have discussed the random forest, which is nothing but a bagging sort of an approach. And we discuss as to why we don't go for a random forest approach, because whenever tabular data is involved and non-linear relationships are involved, boosting, where each weak learner is sequentially improving its own errors, is considered better. So now we have done it all. Now we just need to go through a model. So today I chose a gradient boosting model. Others can be chosen as well, and actually the XG boost is the strongest out of them. But we don't move like this. We first create a base model and then eventually move up in order to, uh, go for models which are stronger in nature. Again, it all depends on the type of data that we are using and the problem that we are solving. In some cases, this ADA boost model might prove to be the better one, or a cat boost model. We have got the no free lunch theorem, which basically states that there is no single model which is the strongest or gives us the best answers. It all depends on what problem we are solving, what constraints we have, what features we have on our hands. Okay. If theoretically you have a question, XGBoost, you can close your eyes and answer. It is the most mathematically sound, the most elegant boosting model to ever exist. Okay. Gradient boosting is the simplest out of these five, which is why we are implementing it as the first model. So without wasting time, let me quickly go on to what? To finally we are going on to it. To what? To nothing but the gradient boosting physics. What does the gradient boosting model do? Very quickly, I'll get on to it. As after that, the physics, we don't have much left. We'll discuss the complexity and the code and be done with it. So let me go on quickly. Let's pick a white pen for the math. It is always amazing. So very simple, like I said, that a boosting model, let's say that this is my model function. Okay. So what will it look like? Like I said, that it is taking the prediction from tree 1, then tree 2, then tree 3, and what? And so on till whatever number of trees I have chosen. Let's say M. M can be anything. It doesn't matter. Doesn't matter. That's not the point here. Okay. This reduces bias. It improves generalization of a model very well. As you know, basically our model is learning from the errors of the past model. And it is a bit slow. Why is it a bit slow? Because this is not parallel in nature. This is sequential. We have to first completely train the first model. Then the second one is saying, okay, what are your errors? Okay, now I'll train from it. Then the third, then the fourth. So it is one by one by one. It is very slow. It is painful if you look at it. But this is why it makes it very strong, because it leads to eventual better generalization. So let's discuss further as to what is happening when we implement this model. Okay. Now, every model has a loss function which we need to minimize. A loss function is nothing but, let's say I predict some value, that this is the value of the insurance, and then I check the original data that this is the original value. So the difference between them, the difference between the actual value and the predicted value is the loss. And I need to minimize that loss. So how will we go on doing that? Let's discuss it. So we want to minimize nothing but the loss. Now, what will the loss look like? The loss will look like nothing but, let's say, this. Okay. This is what the standard loss looks like. This is the mean square error loss function. Okay. I've written it in a different way. Y is the actual values, fx is what we have predicted using this. Okay. You can write it in some different way that you like as well. But just for the sake of this, I've written it like this. Now we need to minimize this. So how do we, minimize such things? We just take the gradient or like the derivative. Like we know this from 11th grade, if you need to minimize or maximize a function, which means you need to optimize a function, and there is no other constraint. You just need to optimize it. We simply take the derivative and then we equate it to zero. So we'll be doing that, but first I want to discuss something. So, let's say that you get a simple model, like a simple tree model as our weak learner here. It looks something like this, and it is nothing but the mean of y, which means the average of y. So I'm writing this in a box. This is nothing but another way to write it, another way to interpret the results of a weak learner that we have chosen here. Okay. Now, we calculate the residual error. What is the residual error? Basically the remaining error. Residual means remaining. So this is basically the difference between the values that we predicted and our original model. So let's call it R1 to look nothing like Y. Y is, our predictions, and then F naught of X, which is nothing but the mean of all the Y predictions. So this is what the residual will look like. Okay. Now, let's combine this. How will the model updates happen? So the model updates, you can say that when the model will try to correct its value, it will look something like this. F1x will be the new value. So it will be nothing but the value of, the tree one. This is what it will look like. This is how the updates will look like. Okay, eta is nothing but the loss. Eta is nothing but the learning rate in this case. Now this is for one tree. Now when we repeat this process for m trees, what will happen? What will happen? So when we repeat this process for m trees, it will look something like this: f of m as a function of x is equal to the initial model residual. Okay, the initial model that we took, f naught x. It's like the mean of a simple model, f naught x. Okay, combined by eta summation of all of the m trees. Okay, this is what it will look like. Okay, when the model is running for m trees, this is what it will look like. So this is the first model, the first basic tree or the weak learner that we get. And then every time when the model is running, it is learning from the errors of the past tree. Hence, we have written it as a summation of the m trees. Okay. Now, very important, like I said, that we need to optimize the value, which means, we need to maximize or minimize the value of this loss that we had here, this right here. So how do we do that? So we do that simply by taking the gradient. Okay, this is how the model learning intuition will come from. So when I take the gradient, which means like the partial derivative of loss with respect to the function f, what I get is nothing but, let me take the function from here, y minus fx whole squared. So I get nothing but 2, okay, multiplied by y minus f of x. Okay, which means that this is sort of like the value that I need to minimize, this value right here. Why do I need to minimize it? Because this is the loss. And the lesser the loss is, it means that our model is a stronger model because our predictions are closer to the actual values. Now, looking at this very carefully, let me quickly try to explain the intuition of gradient here. So, what is gradient here? Gradient means nothing but the slope. The slope of what? The slope of the loss with respect to the function that we chose. So, what happens is that whenever we talk about gradient based learning, which we are doing here, we are talking about loss as, the steepest gradient. Okay. So let's say that this is your graph, any basic graph, and this is your function, the loss. Now, what happens is that this model will go on and it will calculate the slope at different points. Maybe it will calculate at this point. So it will look something like this. Maybe at this point, so it will look something like this. Then at this point, so it will look something like this. And it will calculate it for all of the points. And what it's asking basically is that what is the direction of the steepest slope? Which of these slopes that we discussed right here is the steepest? Now, why are we going for the steepest? Because the steepest slopes indicates the highest value of loss. Okay. And what will that tell us? If we know the highest value of loss, we can train our model appropriately by going to the opposite of it. What does this mean? Let me explain it to you. So, let's say I got a loss value of -5. It means that my prediction and the actual model it is off by -5. So, if I draw it on the number line and I have 0 in the middle, this is -10 and this is -5, let's say. This is 5 and this is 10. Okay. And I have my loss right here. Okay. Now I ask you that, this is the loss that I'm getting. How do I update my model? How do I make my model better? You will say this simply that the loss needs to be 0. Okay. So the loss needs to be 0. So what do? We move this loss to the opposite direction. Simple as that. And when we look upwards, how did we calculate the loss? We calculated the loss by taking the gradient. So our loss is nothing but del L by del F, which is equal to 2 into y minus f of x. So this is our loss, and to minimize it, we try and go to the opposite of it. So mathematically, to go to the opposite of it, we just add a minus sign to it. Simple. So this is eventually what the model will be training on. Every time it will calculate the gradient to get the steepest direction of slope. Okay, and the steepest direction basically means that that is the area where the model is having the highest loss and we need to reduce that loss. So how do we reduce it? By moving to the opposite of it. How do we move to the opposite of it? By adding a negative sign. Simple as that. Okay. This is the way that the function slowly and slowly, step by step, sequentially moves to the direction of the true function. Okay. So, the concept of learning rate also comes in here. So let's say that this is the new value of the function and this is the old value. So now I add eta to it. Eta is nothing but my learning rate. And then I multiply it by my loss, the direction in which I need to go. And I'm going in the opposite direction. Why? Because I want to minimize the loss. This is what will be happening eventually. This f dash is, you can rather write f new here and f old here. It will be much more intuitive and easy to understand. So the old value will be added to this update, and this update will be having a minus sign because we want to try and move opposite to the direction that we were before. And this way we will get the new one. Then again it will happen for the second tree, then the third tree. This way sequentially all of the times the error will be reduced and reduced and reduced until we eventually go on to the direction of the true function. Okay. Model results and the predictions. Okay. So this is it for the model physics. This is how the model was eventually working like. So we have discussed like a ton of concepts in this and we haven't even gotten to the code yet. This is why I said this will be like a very concept heavy video. Okay. Now not much work is remaining. So now we go on to you can read this basically, guys. This is कितनी देर हो गई? 1 घंटा होगा कोई बात. So guys, you can read this. This is pretty basic. This is gradient boosting over linear regression. This is the same that I tried to explain as to why we choose gradient boosting. So linear regression is very simple. It basically tries to fit everything on this line. And well, real world data is hardly like a straight line. Okay, it is very, very non-linear. It is unpredictable. Okay. So the issues happen, which is why we don't choose this. You can read all of this. I'm not reading it again. It's the same thing. This is the math that we implemented. It's the same math. I have included all of that in the whiteboard as well. If you want like the formal results or something, you can read the repo. It's the same thing that I've explained. Okay. This is how the gradient descent is working like. This is, I explained how the loss function will look like, why we at the negative direction. Okay, all of the intuition. And this is how the model updates look like. This is the same thing that I explained to you right now. Okay. Now, very important, key hyperparameters. Now, since we can say, we are using trees and we are using trees in a sequence. So the hyperparameters are the same ones which are used in a decision tree model. So that is what we are doing right now. So the three most important ones, we have got the max depth, which means the maximum depth of each individual tree. So we can take shallow trees, which means, very small trees as weak learners, and then we can combine their predictions to get our final answer. We don't take trees which are very deep because deep trees are strong in themselves and they might lead to overfitting in the data. Okay. So then we have got the N estimators. This is the number of stages in the boosting, which means, how many stages do you want to boost your model by, which, like I said, that we keep boosting until we converge, which means that the error becomes zero or close to zero, the loss becomes zero or close to zero, or the number of N estimators are fulfilled. Let's say I take five estimators, and if it is boosted five times, then it stops. Simple. Learning rate controls the step size. As we know, we have discussed this rate a lot of times. So every time when the model will, try to update itself, which means, let me show it to you in the graph. So this is like the error that we are having. Now, model will try to move opposite to this, or if it calculates this as the steepest slope, it will try to move to the opposite of this. Now, by what extent does it move to the opposite of this? By what value? That is controlled by the learning rate parameter, which is represented by eta. This is the Greek symbol eta. Okay, it is called as eta. It is controlling the learning rate. Okay. Again, too high of a learning rate will not be good for the model. The model will converge very, very, very quickly, and it will basically lead to underfitting, and the model will not learn pretty much of anything. Too less, and what will happen is that the updates will be stable, but the model might underfit. Okay, and if it is too high, the model might overfit. Typical values. Okay. This is, I have mentioned a few values here that this is how you can choose some values. This is all intuitive, by the way. We try and choose the learning rate based on GridSearchCV. I will explain that. So this is what we, have done. So we first make a baseline model where what we do is, like I said, that we have got these three hyperparameters. So what we do is we take three manually chosen values, which means these values you can enter yourself in the model for this. So I take 200 as the n estimators, zero point zero 0.05 as the learning rate, and the max depth is 3. These are random values. This model might be strong, it might not be strong. We do this to get a baseline, and then we can optimize our model to compare it from the baseline. This is how we do it in standard machine learning model pipelines. Okay. So we do this, we calculate the time for it, and basically these are the metrics for this baseline model. Now, of course, the baseline model is not very strong. So now what we do is we do something called as hyperparameter tuning. This is not the first time we are implementing it. We have done this using GridSearchCV. So this time we take three logical values of n estimators, three logical ones of learning rate, and three logical ones of max depth. You can take five as well. You can take 10 as well. The more you take, the more computational power will be required by the model. Okay. And by logical values, I mean that no need to take values that don't make any sense. Take values which are close to the model and which make the model converge pretty quickly. Now, what will happen is the model will run for all combinations of these values. So three, sorry. So, three, then three for this, then three for this. So model will run a total of nine combinations, and it will figure out which one gives us the best one of this. Okay. This GBR.best estimator gives us the best set of values for this, which I have discussed later. This is the inference latency and training time. We can discuss it. So of course, for the Grid Search CB1, it is going to take a lot longer because we are doing a lot more combinations. Okay. This is, let me quickly show it to you. This was the results between the baseline gradient boost, and then the tuned one. So you can see the root mean square error is a bit higher in this case. The R2 score is a bit lower because the tuned one gives us the final values. See the training time. Of course, the tuned one runs a lot more combinations, so the training is less. This is the residual plot. It plots the errors compared, okay, of the tuned model. This is a feature importance matrix. I've included this all in the repo. You can read it, you can check it out. So, being a smoker or being a non-smoker was the most important feature in order to land out correct predictions in the baseline model. In the tune model, again we can see the smoker being yes or no as a smoker is the most important feature. Okay. This is the boosting stage error. So basically, this tells us as to how the mean square error is increasing or decreasing with the number of iterations. So we can see that eventually it explodes up too much between 0 and 20 iterations. Then between about 20 and 40, it almost comes close to 0. So this converges very smoothly, which means our model is pretty strong in its predictions. This is the best set of parameters that we found using GridSearchCV. I did not have to lift a pencil doing this. The model ran all combinations and it said, okay, this set of combinations is giving you the highest value of, the metrics which we chose as R2 score. So these are the best values that we achieved. 100 n estimators to depth and zero point 0.1 learning rate. So this is very good. You can check out the code. It is handwritten code. It is very intuitive, very logical, it's very straightforward. It has nothing special in it. Pretty readable code. Okay. This is the set that we give. N jobs is equal to -1. Basically, this is to control the number of processors that we allow for a problem to happen. So -1, when we assign it, it means that the model can use as many as it wants. Cross validation is equal to 5. I have discussed this. So rather than, let's say we have got a 80-20 split right here. So this is 20, this is 80% of the training, 20% of the testing. So rather than choosing this set all the time, the cross validation will choose a different 80% every time. This is 80, this is 20. Okay, next time it will take something like in the middle. Like it will take this 80 and this 10 and 10 will be like the testing D. And it will do this 5 times. Okay, every time it will get some answer. It will get some answer from here, from here, from here, and from the other two as well. The final answer will be an average of all of them. So this prevents overfitting and gives us a very generalized model. So this is again a very good idea, the idea of cross validation. Okay. So we have done this in here as well. Now we quickly get back to the repo. This is the hyperparameter tuning. This is the same thing that we discussed right now. You can read it. These are our metrics that came out. Feature importance matrices, boosting stage, residual analysis, time and space complexity. Very interesting. And we are going to quickly analyze this. Now, let's discuss it slowly. Okay, this is very good as I don't think anyone else does this, but it is the most exciting thing to do. So, we are eventually using baseline decision trees to train our model. And like we discussed in the beginning of the video, it takes nothing but a time complexity of big O of n log n for a normal decision tree model. And what's the reason for that? The reason is pretty simple because eventually we are sorting all of the nodes to decide which one to use for the split in both the ID3 algorithm using gene impurity and the CART algorithm. Sorry, in the both the CART algorithm using the gene impurity and the ID3 algorithm, which uses the information gain or the entropy in both of them. So it is n log n, but is it truly n log n? So if we analyze this, it is n log n for a single tree. Now let's assume in our current model, we have got a total of t number of trees. Okay, sure. Now, like I said in hyperparameter tuning, let me quickly get back to it. Like I said, we are using 3, 3, and 3, which means 9. Okay, 3, 3, and 3 combinations. So we are using nothing but 3, 3 and 3 combinations every time. Okay. Every time we are using 3 different combinations. And we are using a cross validation of 5. This is going to be the eventual time complexity. So if you write it, it's like 27 into 5 into t into n log n for the sorting. Okay. 27 into 5, you can calculate it. It is nothing but 135. So 135 t into n log n. This is the time complexity. Okay. It is very important to analyze it like this because this is how you can reduce it. Earlier, we were just taking it as this. Now we know that this also contributes a significant amount to it. Now we are almost reaching to the end. This is how you can understand. I have taken the same things in the repo. You can read it. This is the prediction complexity, typical. Space complexity, again, we need to understand what the model is storing. So whenever we are making a split, the model stores all T trees in the memory. And each tree has a depth of 2 to the power D. Why is it? Because trees scale logarithmically. Okay, so one tree splits in two nodes. Then the two again split in two here and two here. So it looks like, if I quickly show it to you, like this is the original node. Okay, it splits like this and this. And then this again splits like this and this. Okay. This again splits like this and this and this and this. So this is like 1, which is 2 to the power 0. This level is 2 to the power 1, which is 2. This level is 2 to the power 2, which is 4. This level is 2 to the power 3, which is 8. Okay. So you can see this. This is how it is scaling like, which is why every node in every step is nothing but 2 to the power d, where d is the depth, which is why this is the space complexity. Now, as a part of the final thing that we need to discuss, uh, this is the last thing in the model. What are the failure cases? What are some cases where our models, which we have used today, gradient boosting model, will fail? Okay, let's quickly go through them. So you can read it as well. This is easy to understand. So what happens is that in some cases, when we are going through to calculate the insurance expenses, there are some very high cost individuals. Okay, and they give out positive values, highly positive values. Now this leads to this basically leads to an extreme expense outlier problem. Now, outlier is something that lies outside of the mean values, which means either a very low value or a very high value. So this basically what happens is that model will sort of underpredict high expenses because gradient boosting tries to minimize the average square loss. Hence, it will try and underpredict these high values, which will eventually cost us some customers in the future. Okay. We have got overfitting with too many trees. This is the simplest failure to understand. So, boosting requires training trees sequentially. So, if we take too many n estimators, which is the number of trees that we selected, the model might start to fit the noise in the training data rather than, the true values and the true signals that we need to capture, which is why we use GridSearchCV to very carefully get a good value of n estimators. Okay. We have got extrapolation failure. So this is pretty important. So if a new sample for a feature has a value which is not in the training range, which means it is outside the training range, the predictions will be unreliable. It is explained in the repo with an example. So, if a data set has ages between 18 and 64, but let's say that for some values, the age goes outside. So for that, the model has no basis for prediction and it will basically produce very unreliable estimates and it will give no warning to it. Okay, so this is very important. Now, as the last one, some feature interactions might not be covered. Since, like I said, gradient boosting is very strong in handling non-linearity in tabular data. But if small and shallow trees are used, then, uh, some non-linear interactions can be missed. Okay, sort of higher order interactions such as, age, smoking status, BMI, they might be related. But since we are using very weak learners, okay, and they are very shallow trees, which cannot really capture these high order interactions, these high order relationships between the features. Our model might miss it. Okay, deeper trees will capture them, but they will eventually increase the overfitting risk, which is the trade-off that we have selected in here. Okay. So this was it for day 8, a very detailed model. And you can check out the repo. Now I will meet you tomorrow